All right, so these are the direct comparison test. So what we've already done is we've talked about the nth term test for divergence. Remember, the nth term test is only a test for divergence, and it says if the limit's not equal to 0, then the series diverges. And think about it, if the limit's not going to 0, let's say it's going to 1, then you're going to keep adding 1 and 1 and 1, and it's going to be divergent, which means infinite sum. We also had geometric. Geometric said that if you had something like this, it converged if the absolute value of r was less than 1, diverged otherwise. And the other one was p-series. And p-series look like 1 over n to the p, and if p is greater than 1, it converged. So keep those in the back of your mind because those are kind of your basic ones. So the first of the comparison test is called the direct comparison test. So what this means is you're going to have a sequence that you know and a sequence that you're going to compare it to. If the one you compare it to converges and the sequence you had was smaller, then it would also converge. But if your sequence is AN and they told you it converged, you can't say anything bigger about something bigger than it because something bigger than it could diverge or it could converge. Same thing the other way. If I know BN diverges, I can't say anything about something smaller than it, but if AN diverges, I know for a fact BN has to diverge. So it's all about getting the bound appropriate. So looking at this, the first thing you want to look at is, what does it look like? To me, it looks most like a geometric. It's not a geometric, but I think I could compare it to one. Now, sometimes you're not sure if this is really true. This is what we want to be true because this converges, so we know something smaller than it would converge. The other inequality would not work. So what we do is the double flip this one, change the direction, flip this one, and that's definitely true. So we know this inequality is true. So since it's less than a convergent series, it also converges by direct comparison test. Same thing here. This looks most like a p-series to me, and it's a divergent p-series. So what I want is to show that it's bigger than that. And when you flip it over, that's true. This is a divergent p-series, so anything bigger than it would also diverge. In factorial, now that doesn't look like any series we know, but we know factorials grow so fast. We know a factorial is going to be bigger than n squared after like 3 or 4, maybe 3. But after that point, it's always bigger. So that's all we care about is after some point, is it always bigger or always smaller? So we know that it's less than a convergent series, so therefore it converges. And this is kind of the most famous thing that you use it for. We know that sine of n over n squared, if I take that and I wrote the absolute value of that, so I can say this right here is the sine over n squared, and I know that's less than or equal to, definitely less than, but it doesn't matter, of sine n over n squared, because the absolute value is only going to make it bigger. Well, we know sine is never bigger than 1. That's a bound that's always true. So this would converge by DCT because we compared it to a p-series. So what things we can bound, we know that sine and cosine can be bounded by 1. And the other one you guys love to forget is that the arctangent is bounded by pi halves. Now the direct comparison test is kind of like my least favorite. It works really well a lot of times, but other times it's just hard to pick something that you can show that it's the correct inequality. So the next one is called the limit comparison test. So what you're going to do is you're going to have a sequence, and again, you're going to find some other sequence that looks similar to it that we know something about. If the ratio of those two, if that limit is finite and non-zero, then the series converge or diverge together. So if your comparison series converge, so does your original one. If the one you compared it to diverged, so does the original one. What this is saying right here, this limit, it's saying that they're changing at the same rate. AN and BN are either going off to infinity together or they're going to, converge to something else. Okay, so looking here, and again, right here, with a DCT, I would think I'd have a hard time to figure out what I would have to compare it to and show the inequality. So all I do is look at the degrees. The degree of the top is n squared. The degree of the bottom is n to the 5th. So this series is basically behaving like this p-series. Now I'm comparing it to a convergent p-series. So as long as my limit is finite and non-zero, it converges also. So you take this, and it doesn't matter which one you put on top, multiply by the reciprocal. But now look at the degrees are equal. If the degrees are equal, then you're looking at the ratio of the leading coefficients, which is not 0 or infinity. So they're changing at the same rate, which means they both converge. This is a convergent p equals 3. So now this converges by the limit comparison test. When I kind of know I'm going to be using the limit comparison test is when it looks like a rational function. Now, it's not really a rational function because it could have square root powers or fractional powers or whatever else, but it kind of has that shape. So here, the degree of the top is 1. The degree of the bottom is 4. So again, overall, this is 1 over n cubed. So I take my first series and I multiply by the reciprocal of the other, which shows the degrees are equal. N to the 4th, n to the 4th. So it's the ratio of leading coefficients, which is 5, which is not 0 or infinity. So this converges by LCT. And you got to remember to say that this was also a convergent p-series. All right, so kind of just more examples. Again, it looks like the square root of n, so that's what I'm going to compare it to. It's a divergent p-series. Looking at the ratio of the reciprocal, it's not 0 or infinity. So since the one you compared it to diverged, the original one diverged. Degree of the top is n. Degree of the bottom is n squared. So overall, it's 1 over n. That's a divergent p-series. And again, the limit's finite, non-zero, so they both diverge. Now here, I wouldn't even go to the limit comparison test or direct comparison test. Looking at this, the top has got an exponential. That's going to grow a lot faster than the bottom. So immediately, divergence by nth term test. And again, another limit comparison test. So multiple choice. Which of the following statements about convergence of this series is true? Okay, well, first thing I'm going to look at the things. It says I'm going to compare it to 1 over n, and it says it converges. Well, 1 over n diverges, so immediately I know that's not right. Here, you're comparing it to 1 over n, and that diverges. Okay, so I can keep that one. This one I'm comparing to n to the 3/2, which is bigger than 1, so this one converges, so I know it's not C. So that's not true. And then here, this one diverges, and they told you it converged. It has no choice but to be D. Which of the following series converge? And again, I didn't go through and actually do all the steps here. This one converges because I'm comparing it to 1 over n squared. This one diverged by nth term test. The degrees are equal. This one I would have compared to 1 over n, which diverges. And this one, the exponential on the top is bigger than the exponential on the bottom, so it's going to diverge, or you can do nth term test for divergence, or you can compare it to the geometric diverges. Use a limit comparison test to determine whether this converges or diverges. Well, what does this look most similar to? Looks most similar to 1 over 5 to the n, which is geometric, a convergent geometric. And they said use a comparison test. Well, I think for here it'd be easier for me to do a DCT because that bound is pretty easy to, you believe it. So it also converges. This is often how you're going to get the DCT on the test. So we've got a series AN and BN. They're both non-negative. If AN diverges, which of the following must be true? Well, if AN diverges, then if BN was bigger than it, would also have to diverge. So it's not true. AN diverged, so anything smaller than it, we can't say. If AN diverges, then anything bigger than it would also diverge. So it's B. So it'll be more on checking the inequalities and making sure you have the correct logic. And just another one I'd compare to 1 over n squared. And I think the hardest thing when you first start this section is trying to figure out what to compare it to. But again, go back to the p-series, the geometric, the nth term test. This looks most like geometric, so I'm going to compare it to a convergent geometric. That inequality is true, so it also converges by DCT. P-series diverges. I would compare this to 1 over n cubed, which converged, so therefore it will converge. I would compare this to 1 over 4 to the n, a geometric, which converges, so therefore it would converge. So only the first one diverges, so A. Just skip number 17. Well, you can talk about it. We want to know which values of P does this also converge for. So I just kind of went through and I said, well, okay, well, let's kind of look what P is. We could have done all these limits. It's so much worse. But I know n squared natural log of n has got to be less than that. This one I know diverges. So here I would just check it by just showing the inequality, because we know n squared natural log of n is going to be bigger than n natural log n if you flip them over. So here we have AN is less than BN. If AN converges, we don't know. If AN converges, we know nothing about something bigger. If AN converges, again, I don't know. If AN diverges, then we know BN diverges. That's true, because divergent means an infinite sum. So this right here is trying to tell you something about LCT. The AN and BN are the ratio, the limit of those is 2, so they're telling you that they compare. So we have the series AN and BN. We know they compare. So if they compare, this is limit comparison test because the ratio of the limit is finite and non-zero. Then they both converge or diverge together. So this one says converge, diverge. No. Diverge, converge. No. Converge, converge. Yes. Diverge, diverge. Yes.